In this video, we'll spend some time looking into some of the differences between simple and multiple linear regression. As I stated before, there's a lot of similarities, and in fact, if you have a good understanding of simple linear regression, multiple follows pretty easily from simple linear regression. However, there are a few things that we want to make sure to keep in mind, keep focused on as we move to some of the intricacies of multiple linear regression. This video is going to look into those differences so we're able to bridge that gap a little bit easier. The first issue that we're talking about is called multicollinearity or collinearity. And this is actually one of the oddest or probably the most difficult difference between the two. Essentially, collinearity means that my predictors, the x variables, can be predicted well from each other, from the other predictors. And that actually causes some problems in our model. We do, and I'll just draw your attention to the bottom of this slide very quickly. It says that the x's should be correlated with the y. We want the x's correlated with the y because then we can use them to predict or to understand relationships. But the x's should not be correlated with each other. And the reason is this collinearity or multicollinearity issue. It basically is stating that as the strength of the relationship, when those predictors start to become very, very similar, they actually, similar meaning correlated in a sense, because if I can predict one from another, they're not really giving me new information. And if I'm not getting new information, it's redundant. And not only, normally you'd probably think, well, hey, if I get redundant information, no big deal. I'll just kind of ignore half of it and everything will be fine. It's just doubling up. It can't hurt me. Well, from a mathematical standpoint, it can hurt us because of some of the minimization of errors that's happening in the background. If you have things that are too redundant and too collinear, it becomes very difficult to estimate them individually. Because in the multiple regression framework, we need to estimate a slope for every single variable. And if I have two variables that are essentially the same thing, it's really hard from a mathematical standpoint to kind of assign, well, who gets credit for what? Does variable A or variable B? How do I use it when they're really telling me the exact same things? This actually takes on some very weird aspects. In fact, when we look at this, everyone says, well, okay, what does it mean? What is going to happen? And honestly, what's going to happen is some weird stuff if you have things that are highly correlated in your data set, x's that are highly correlated with each other. The coefficients have inflated standard errors because of this correlation, and that leads to some very odd results. I want to, again, emphasize one more time. Correlation of the x's with the y's is a good thing. A lot of people take from this that we don't want correlation. No, we do want correlation of x's with y's. We don't want correlation of x's with other x's. Going forward a little bit more, it says basically we get very unstable estimates. That if you have things that are highly correlated, you can get drastically different results. And we want to have some semblance of consistency. But what happens is, if we actually have this collinearity problem, the consistency of our results is not necessarily as guaranteed. The reason being, it confuses the model. It can't divvy up credit. So it's just a very odd concept. I'll try to give an example in an upcoming video or maybe in a project to see it. But it is something that you need to be aware of simply for the fact that you could get some contradictory results. I'll actually talk through one example. I could say, let's say I want to predict income. And I want to predict income using age. And I find, hey, you know what? Age is a great predictor of income. And my friend said, well, I want to predict income too, but I'm going to use the year you were born. And if we see the year you were born, you'd probably say, okay, that's kind of the same thing as age. But that actually does a really good job of predicting as well. So we put our heads together and say, let's go ahead and try and predict using age and the year you were born. Because if they both worked well separately, they'll probably both work even better together. And actually what comes out of the model is just kind of a jumbled mess. It turns out nothing significant, and it's very confusing results. Individually significant, but as a group, insignificant. And that's something we have to be aware of going forward. Now, how can you measure collinearity? Yes, we can see if the x's are correlated with each other, but sometimes collinearity goes a little deeper. It actually says that Two variables may not be collinear. They might not directly have a high correlation. But a combination of two variables might be collinear with a third variable. And it gets somewhat, I would say more than somewhat, it becomes very complex. Well, there's a statistic to help measure collinearity of our predictors. And it's called the variance inflation factor, or the VIF. This is just a simple check to see if our predictors are highly correlated with each other. R square in this model, it's 1 over 1 minus R square. And you might say, okay, we saw R square. We know what that is in the simple linear model. In the multiple model, it's the same thing. But this R square is actually a little bit different. This R square says, remember what we're looking for here. We're looking at how related the x's are to each other. This R square, what it does is it says, I want to know if I can predict, let's say, x1 from all of the other x's. So we're ignoring the y completely when we figure out the VIF. If I predict x1 from the other x's, I would get an R square for that. And that R square is what goes into my VIF calculation. You notice that if the R square is close to 1, it's saying that I can predict x1 pretty well from the other ones, the other x's, in which case my VIF would be a very large number, and large VIFs are a problem. If my 2 predictors or 3 predictors or 4 predictors are independent, it's saying, you tell me what x2, 3, 4, 5, and 6 are. I can't do anything. I can't tell you anything about x1. That's actually a better scenario, and our VIF becomes 1. Remember I said collinearity can lead to inflated standard errors. This is in an essence how those standard errors are becoming inflated is related to the variance inflation factor. Now, how do you get this in R? Because nobody wants to have to run extra regressions to check are these predictors correlated or not. Well, there is a function that you say VIF is the function, and into that function you put the model itself. This is not in standard R. It's within a package that's a car package. So make sure you install in library the car package. Once you do that, you can calculate your VIFs very quickly. Now, really, what do we need to know about the VIFs? Well, small is good, high is bad. Well, what is small, what is big? Well, if you have no correlation among your variables, the perfect scenario, R square is 1 or is 0, and therefore my VIF is 1. That's the best scenario I could ever have it. And honestly, that only arises when you design an experiment. If I don't design an experiment, if I sit there and I'm actually just measuring things, oftentimes we won't get a VIF of 1, but it will get larger. So we say, well, how large is acceptable? And usually we would say if the VIF gets above around 4, you start to get a little bit worried. You don't necessarily stop, but you start to get a little concerned. If you see VIFs bigger than 10, it's usually a good indication that maybe you have too many redundant variables. Maybe just take that one out. And it's interesting how taking out a variable can actually improve the fit of the rest of your model. It isn't about that kitchen sink model where you threw everything but the kitchen sink into the model and that's going to be the best. It actually turns out you can get better models by not including things that are either useless in prediction, as we saw how to test in the simple model, or redundant, this collinear type idea. Now, the second concept that I want to discuss in this video is about a slight modification to the R square term. Before the R square, recall, was the proportion of variance explained by the model. How much better did we do than a flat line, is what we said. Well, there's a little bit of a downside with R square. It basically says that every time you add a new predictor to the model, you will either increase your R square, or at the very least, you won't decrease your R square. It only can go up. And the reason for that is you can't unexplain variability. So if I'm plugging things into my model and something is useless, absolutely, utterly useless, well, what will happen is the beta in front of that will be 0, and I can still have the same exact explanatory power. I never go downwards in terms of my proportion of variability explained. And that's kind of a problem, because if I want to say, well, which model's better? I usually say the one with the higher R square. Well, if R square always gets bigger, I'll just keep throwing things into it and I can never hurt myself, and that makes it more complex, and I don't want more complex. So if I get too complex, it doesn't generalize, so we'll see more on that coming up soon. So I also have to consider some other problems. When I put too many things in the model, it makes it more complex, and that actually loses what we call degrees of freedom, which we're going to see near the end of this video. And that can actually hurt our model as well. So even putting more stuff in could be potentially detrimental. In other words, everything that I put in can only increase my explanatory power. But it also makes my model more complex, so I have that trade-off. The degrees of freedom are kind of a measure of complexity. So if I say if I can increase the r-squared by a lot, I'd probably want to keep that variable. The balance is in favor of more explanatory power. If I don't increase my r-squared by hardly anything at all, I'd probably say the balance of power says you're making it complex for no reason, don't include it. So we need to figure out a measure that kind of accounts for that, and that's called the adjusted r-squared. The adjusted r-squared, here's the formula. I don't expect to ever make you calculate this. But the adjusted r-squared simply says, all right, fine. R-squared, it goes up. You get more explanatory power when you put something in there, into the model. But every time you put something in the model, I'm going to charge you for it. It's going to cost you. I'm going to take a little bit of your r-squared away. And the reason for that is I want to make sure that if you put something into your model, you're not throwing something in there just for the sake of putting it in there. You're putting it in there because it's actually worth something. And the way I can kind of measure worth is I'm going to charge you for it. I'm going to lower it every time you put a new predictor in. So what this does is it says, if it's worth it, the benefit outweighs the cost. If not, the cost outweighs the benefit. So now I have an r-squared, an adjusted r-squared value that I can compare apples to oranges. I can say, well, your model has 2 predictors and you have an r-squared of 70. My model has 400 predictors and I have an r-squared of 71. Some people would say, oh, well, the 71's better. But then I could look at it and say, wait a minute, you have 400 variables, I have 2. I kind of like a simpler model that probably is going to generalize better. Adjusted r-squares in that case would likely be, let's say my adjusted r-squared for the model with 2 has an adjusted r-squared of 69, and my adjusted r-squared for the model with 400 has an adjusted r-squared of 50%. Now it's letting me compare them on equal scales, even though they have different values. Computer programs will give this to us. It'll be no problem to actually interpret this as we move forward. The final addition that I want to bring up is the ANOVA section of the regression. Now, we have not spent any time in this class on ANOVA. However, we have talked about partitioning the variability. When we talked about partitioning variability, we saw that graph and we said, how much of this graph, how much of the variability would I get from a flat line, or basically saying no predictor at all is worth anything. And then I said, okay, compared to that flat line or flat plane or no predictor is significant, how much better is my model? How much did I reduce the variability? And that was our r-squared term. Well, we can actually run a test to say, was our model worth it? Was there a significant reduction of error by the addition of our parameters? And we actually get a p-value from this as well. P-value tells us if the x variables, and when I say x variables, I mean all of the x variables, have any explanatory power whatsoever. If the p-value is small, then that means that there is some value in what you did. Something seems to be worthwhile. Your model is significant. Now the question is, what in my model is significant? What components are significant? And you know what? We've already talked about how to do that. We can do the t-test. So actually, the t-test for each predictor. So what we're doing here is testing either everything is not significant, that's our null hypothesis, the model has no explanatory power, or the model has some explanatory power, at least one of the betas is different from 0. I don't do a whole heck of a lot with this test often because I'm more interested in prediction, and I kind of want to see, I want to look at each individual predictor and say, is this one good? Yes or no. Is this one good? Yes or no. Rather than look at it in a holistic framework. But sometimes it can save you some time. If the F test, this ANOVA test, says nothing matters, then why do I need to go and look at all the different pieces separately? I would say, look, it's just not worth it. This is not a good model. Try something else. So let's hop over to R really quickly. I'm not going to do a very long demonstration here. Drag this over here. And as we talk, we're going to continue on with this model here when we said we want to do some sort of a model with this cars data, and we predicted the miles per gallon from the weight. Well, let's try and make it a multiple regression model. So let me come down here, and I'll call this cars multiple, or mult. And I want to fit a multiple regression model that predicts miles per gallon from weight. I'm going to still keep weight in there. And let's add a few more things. Like, let's say, you know what, I also want to know if the horsepower helps predict the miles per gallon, or maybe the what other things are in this data set what else could we use? You know what, let's just leave it with horsepower for now and just say weight and horsepower. Multiple model. When you add more predictors, you simply put a plus sign in between them. Our data set is MT cars. And we'll run the model. Now I can look at the summary of the model. So summary of the cars multiple model. And let's check what we see. We'll come down to the bottom here. And we see our standard coefficient table. And notice now we have a coefficient for weight and a coefficient for horsepower. It was actually pretty easy to do this model. We have the equation, 37.22 minus 3.8 times the weight minus 0.03 times the horsepower. And then I can say, well, are those significant based on the t-test? And based on the t-test, I see over here, weight is very, very significant. And then even after we've included weight, does horsepower add anything? Is it worthwhile? And I'd say, well, yeah, it looks like it's significant too. The p-value is fairly low, 0.001. I have an r-square value, says 82%. And an adjusted r-square of 81%, 81.4. So it penalized me. It said, well, here's how much you explained, but remember, you used two predictors. And you use two predictors, you got we're going to charge you for that. Now, the one thing you see at the bottom, it says F statistic, 69 on this many degrees of freedom with a p-value 9.109 times 10 to the negative 12. This is that ANOVA p-value. This is the model p-value. So here we're predicting we're looking at each predictor separately. Is weight important? Is horsepower important? Down here we're saying, hey, we use weight and horsepower. Was that beneficial? Was that better than nothing? Most times it will be, but you have an extra check. One other thing, if you want to see this ANOVA table and basically see how it breaks down between the part explained by regression and the part unexplained, the error left over, you can use the formula ANOVA, cars mult. We can run that. And as we come down here, we see a regression, an ANOVA table. It basically kind of partitions what is there. It says, all right, well, you know what? Weight explain. We're going to do the mean squared error, or the sum of squared error, I suppose. The sum of squared error is 847. Horsepower got another 83 out of there, and the residuals, what's left over, there's still 195 left over. There are some calculations in the mean squares that we can calculate, which is based on, in this case, weight was only cost me one predictor. Mean square tells me, well, how much did I get? How much bang for my buck did I get? But you see here an F statistic that tells us, are we significant or not? This one actually breaks it down into each variable separately. Now, the final thing you might want to do is check. I wonder if those were correlated variables. Was I in trouble? Well, I could find the correlation of MT cars weight and MT cars horsepower. I could do the actual correlation calculation. You get a correlation of 0.658, and that's a little concerning. I mean, it's that we're starting to get a reasonably high correlation there. I might want to check if collinearity is a problem. So just in case I haven't done it, I'm going to install the car package. And I'm going to use that to try to figure out what the VIFs are. So it's installing my package. While it's installing, I'm going to type library car. It's still installing. I think my computer is starting to fill up with all these videos. Apparently this is a fairly large package, but again, the install only happens once. Okay, now that we're back, because there's a long time loading, I cut out a little section there. I'm going to library the car package, and let's actually spell library correct. And we're in, and now I will run the VIF of my car's mult model. We'll come down here and we see our, even though we had a reasonably high correlation, if you come down here for the VIF, we see 1.76 for both of them. Remember we said bigger than 4 is when we start to get a little worried. I'm not too worried here. Now you might say, well, 0.65, that's a pretty high correlation. And I'd say it's reasonable. Really, when the multicollinearity becomes a problem is usually when our correlations get in the 0.8, 0.9 territory. But even then, it's still worth giving it a look to make sure that we don't have that problem. We'll stop here. I know this is a long video, but I wanted to, this is the main meat of the multiple regression section, because this is where all the new stuff comes from. In the next videos, we're going to look into matrix representations of the model, some of our proofs of where these predictors come from, and then we'll do a case study example where we can see how all these pieces fit together.